So today it's our pleasure to have Gellert giving a guest lecture about planning complexity with QStar realizability. This is mostly his work. So it's just right that he's gonna help us to understand this work better. And regarding questions, so I only got one question and I prepared an answer to that, but I think that we're gonna do that at the end of the class as usual. So with that, let me pass the baton to Gellert. So I stop sharing.
Okay, and I start sharing. Let me see if I can do this. Because okay, 1 second. Okay. Can everybody see this? Does it look good?
Yeah.
Okay, so I prepared a couple of slides. I guess what you guys normally do is you go through the lecture material, and I added a couple of extensions as well, just in case we want to get there. And okay, so I don't know how it normally goes, but feel free to interrupt me if I'm trying to explain something and it doesn't make sense. Then do interrupt me. Okay, so and also I'm not sure how quickly to go, so just you know, educate me as we go. Yeah, we're gonna talk about this thing called planning under QStar realizability, and this is the short name of it. But to expand a little bit, here we have this assumption that you have features such that there exists a theta, such that the product of the feature and the theta is exactly Q star. So that's the assumption that we're going to work under. So you have, for all states and for all actions, you have features, and there exists this hidden theta, and this is a d-dimensional vector. And all you got to do is you got to learn this d-dimensional vector, and if you learn that, then you know all of Q star everywhere. So that's quite simple.
Maybe I'm going to jump in very quickly because
Yep.
the previous lectures, we mostly covered discounted problems, and you might not have known that. So here it's important to, well, important to some degree, but like just to understand the notation. It would be important to talk about like what is the 8-stage problem that you're considering here. It's a fixed
Okay.
right?
Yes, so this we have like capital H different stages here. By the way, all of these results translate to the discounted setting as well, but just because we set up everything like this, you know, we're gonna stay in this notation for this lecture. So we have H stages, which means like you start from stage 1, you then whatever action you take, you enter stage 2, and so on and so forth. And after after capital H stages, like you take an action and you're done. And then Q star is defined in such a way that it is the sum of rewards from t equals 1 to h, and it's not discounted. It's just sum of the rewards. And so we have some special notation on top of this, which is that all the states that we have in the first stage are called S1, and then the second, these are the states, you know, all of these are S2, and so on and so forth. And whenever you have a transition going from any state in Si, it will have to go into a state in Si plus 1. And also we have like Si, I think we have this as well, Sj, there's no intersection unless like I equals J. We have this as well. Okay, and then we also put some indices to Q star and the features, so that like just as you would imagine, the phi h goes from the sh, so it just denotes the stage that we're in, and when we say Q star, we also give it an h, and then we count from h to capital H. So we look at the remaining number of actions to take, and we add up their rewards, and that's going to be our Q star. So now we have this like index here.
Well, of course, for Q star, you have expectations, and like it's the best value that you get with whatever policy, right?
Yeah. It's all of that. So like expected. So like you've got maximum policy expectation over the interaction of the policy. So the R's go according to the policy, and then there's this whole discussion about I guess also about like what does it mean to define an interaction of a policy and an MDP. And in this case, we add random rewards and random transitions, and everything is going to be random as well. Yes.
I have a quick question about the QStar reliability definition there. So we have a theta
Yes.
shared across all time steps.
Mm-hmm.
Is that less general than if we have a theta that's time step dependent?
So it depends on which type of result that it is that you want to get out of it. And it turns out we're going to get a negative result. So like this assumption is a stronger assumption. And if you say that even this assumption isn't enough to do something, then that means if you didn't share your thetas, then that would necessarily be at least as hard as this. So because we're looking to get a negative result, this is the stronger kind of way to formulate the problem. But between the two of them, I mean, you can easily say that like you're going to blow up the dimensionality D. You know, if you don't want to share, like if you have this definition, but you necessarily need different thetas, then you can say you allocate different parts of the dimensionality to the theta. And then you can do the same thing with D times H dimension, right? So when we talk about exponential versus polynomial time or query or whatever, then there's no distinction between the two, right? Because nothing becomes exponential just because you set it up this way or that way.
Yeah, that's fine. Yeah, thanks.
Yeah, cool. I think this is an excellent question because, it comes up a lot of times. And I think it's a kind of a general thing that sharing parameters is the way to go. Like if you prove things for shared parameters, for lower bounds, as explained by Gadet, it's just stronger. For upper bounds, it is at least as strong as the other one at the extra price of blowing up the dimension by a factor of h, which you would have anyways, because then like you have separate parameter vectors. So it's like, really, you should only think about sharing the parameters. That's the only case to be considered, right?
Can you just go over why it's stronger again? Is it because you have like H more interactions with the MDP?
It's because you have D parameters, right? Like you have D parameters in total, whereas if you don't share the theta, then for each stage you have D parameters. Like you have to learn, in this case, H times D parameters.
Right. So it's
in that case. Whereas yes.
Right.
So like here, the assumption is that the entirety of the MDP, at least its Q star, can be you can think of it like you can compress it to D parameters. You only need to learn those two to be able to get pi star out of it. So yeah, okay, cool. Yeah, go on.
I have a question about the SI intersection SJ assumption.
Yes.
So like why exactly we're assuming it, or like what's the implication of this assumption exactly?
It's mainly for convenience. Like you can later say that the state uniquely maps to the stage that it's in, and it avoids confusion later. But it doesn't really matter. Like none of this matters because if you had an MDP which you can re-enter a state, you'd be able to like duplicate all the states and give them individual stages, right? And then you would be able to satisfy this. But the point is, if you satisfy this, then you can say, each transition goes from an S in Si to an S prime in Si plus 1, right? And so then, you can easily just say this, that you're gonna like always accumulate your counter.
I see. Thanks.
Yeah, but it's mainly for convenience. Like it doesn't really matter so much. I think notationally as well, it's going to be simpler. Okay. So the theorem is yeah, so the theorem that we're going to talk about is it is a bit long, and it's got like little constants like this, which don't really matter. But the point is that if you want an online planner that is sound, and by sound we mean is that for every MDP that satisfies this assumption, it can come up with a policy that is delta optimal. So for any such planner, there is an MDP for it, which it will do very badly on, so yeah, we have some further things like values are in 0, 1. Obviously, if you didn't have this, if they were unbounded, then it would be pretty simple to give this kind of bound, but we're not going to cheat there. And what we say, what we mean by it's going to do badly on it is that it's going to take an exponential number of queries. The planner will query the simulator an exponential number of times, exponential in either the feature dimension D or the horizon capital H. And if you were to translate this into the discounted setting, then like this capital H would be something like 1/1 minus gamma. So you can think of it like that. Okay. Is it clear what this theorem is trying to say? It's all good?
Maybe you can go through the rest of the things that are in the theorem statement. I guess there is only one thing. There is only one thing to talk about, which is after the 0, 1 interval, that the transitions are deterministic. But
oh yeah, that's an extra niceness that we say, because it makes the result a little bit stronger by saying that even if the transitions are deterministic. And I guess for context, if so in this case the rewards can be stochastic. If the rewards weren't stochastic and you were able to observe them without any noise, then such a lower bound would not be possible. And I think you guys have probably seen that in the previous lecture. Have you?
no, actually not.
It would. Okay, but that's okay. That would be the optimistic constraint propagation paper, if anybody's interested. It turns out, but maybe it's going to be a future lecture. So I don't know. But it's basically if you.
Right, Galet, you will join us on Wednesday and you talk about upper bounds.
Oh yeah, you know what? Maybe then I will talk about this. So never mind for now. Never mind. But yes, if you have, if you need the spoiler alert, you need the rewards to be stochastic, but you don't need the transitions to be stochastic.
Or the transitions can be stochastic and the rewards could be deterministic.
Yes.
That's maybe a homework.
Or maybe I will. I might actually mess that. Okay. Maybe I won't. Then.
Right. Yeah, it's fine. No,
I be a hint towards the end.
Yeah.
Right.
It's fine.
Okay. So if this is entirely clear, then I guess we could. So I wanted to talk a little bit about like what the principles between the design of this MDP is that will be this like kind of mean MDP that's very hard to solve for a planner. It's actually going to be a class of MDPs, and no planner can solve all of the members of this class, and that's kind of the proof. And then I'll talk about the proof, and I'll try to keep it simple, and we're not gonna dive into the constants, but just kind of the ideas. So yes, what we want is that for almost all actions, the signal to noise ratio, like basically what you can observe about the MDP, it should be very low. Like we'll tell you what class the MDP is in, but to identify which of which member of the class you're interacting with should be extremely difficult. So like we'll tell you some things about the MDP, but they will be all the same across all of these MDPs, such as most of the transitions, most of the rewards will be the same. And whenever something isn't the same, it's going to be incredibly hard to find that, or it's going to be like super noisy and you won't be able to see it. So that's one of the important things here. And so this low signal, yes?
Yeah, so this sentence has two parts, the signal to noise ratio, and it also says almost all actions. So can you say something about that?
Yes, so okay. We're gonna actually construct an MDP with a lot of actions first. Then we'll talk about how to make this. And I think this wasn't in the lecture notes, so don't worry about that. But we'll talk about how to make this work for lower action count. But for what we do now is we're going to have a lot of actions. So many actions, in fact, that you won't be able to try all of them. No planner will be able to try all of them because there's going to be exponentially many. So it's okay to say that one of those actions will reveal everything, and like, yeah, if you happen to stumble across that, then you're done and you solved it. But every other action, everything but that action, will be incredibly low signal to noise ratio. And then yeah, this must hold for all stages that are easy to reach, such as the initial state is easy to reach, and then if you behave randomly or you behave whichever way that you might be able to, then any stage you reach, in particular in the last stage, any stage you reach in the last stage, but in any others as well, this must hold for that too. So you can't. One thing that you can't do is you can't just give all the reward at the end, unless you make sure that at the end those rewards that you will be giving are going to be absolutely tiny. Because otherwise, if it's a bigger number and it's kind of, it has information in it, then you have a problem. So that's kind of an idea behind it.
Got it.
So when I say last stage QStar must be tiny, it doesn't necessarily need to be tiny. It just needs to have low signal in it. So yeah, it might have a constant added to it, but and also, Trevor?
Yeah. So all of this talk about the tiny thing. Yeah, I was wondering about it. I think that you kind of implicitly assume that the worst Q star is 0 and we have Bernoulli's or something like that. And the reward is just Bernoulli. And then if it's a tiny reward with a Bernoulli, then you have to take like inverse Bernoulli parameter number of times the action to be able to estimate that parameter of the Bernoulli. And so that's kind of the idea, right?
Yes. I want I will want the actions to be indistinguishable, and it's easiest to make it like all look like 0 rewards, but I can make it all look like some small constant. It doesn't really matter. But
right.
It's like easiest to think of it as like they'll all be very close to 0, and we'll have this Bernoulli with a tiny mean parameter, such that, as Chaba said, you need.
Yeah, go ahead.
Such that, as Chaba said, you need a lot of interactions to like identify the mean of the Bernoulli.
So if we did it with Gaussians, then it would be like the action gap is very, very small between the optimal action, and all the suboptimal actions give you the same value. Let's say the optimal action sticking out a little bit, and you have a lot of noise compared to the size of the gap.
Mm-hmm.
That should also work.
Yes. And so that's actually an extension that I might get to, is like, can we design a version of this that has a large gap? And that, yeah, but this gap is kind of a nice way to think about it. There's a tiny gap, you won't be able to identify it. And the reason why I said last stage here is because in the last stage, the Q star equals the reward that you get. So like, there's no hiding after that. If the Q star is still large at that, or has more information there, then your reward will be showing. But anyway, I think we should just get to the. For simplicity, again, like this will be super good for us. There's only ever one reward in any episode, so that's good, because the Q star will. The Q value of any policy will be exactly that one reward that you will encounter during the trajectory. Shaba?
One reward means one non-zero reward, so we're kind of basing everything at 0. Okay.
Yeah, cool. Thanks for clarifying this, because I'm being a little bit sloppy here. Okay, so
And like others have to chime in. I'm sure that they're also wondering about this. Okay, good.
Okay. So what we do is we take a lot, and this is like exponential in D, JL Johnson-Linder-Strauss vectors such that they're you take any two that aren't the same vectors, their inner product will be small. However, if you take two of the same vectors, then the inner product will be 1. That's just to say they're unit vectors. They're unit vectors, and they have a small inner product with each other. And you can take exponentially many of these. Was this Johnson-Linder-Strauss business covered before? I think it was. So that's all good. Okay. Okay, so what we say now is like each of these vectors corresponds to an action. There's a one-to-one mapping between actions and these vectors. And we say that there is an A star JL vector, which is always optimal. And so if you play A star, then I'm going to give the MDP is going to give you the reward, which is exactly equal to Q star. And then it will transition, the MDP transitions to an exit lane. And there's going to be no other rewards. Like it doesn't matter what you do after that. And, every feature will be 0. It's fine. Everything is 0. Yeah, and I guess I should say when I talk about a class of MDPs that we designed, the only difference will be the identity of A star. So that's the secret. Like one of them will be optimal. If you play that at any point, you will get all the rewards that you could get in the remainder of that episode. And you're done. But of course, the A star, you don't know what A star is, and that's what the secret is about the MDP. Everything else you're allowed to know about the MDP. Okay. Yeah. Okay. So if you don't play A star, then if you never play A star, then at the very last step, I'm going to give you the reward that is the remaining Q star, right? Just to satisfy that's going to be the one non-zero reward. It's either when you play A star or when you play the last action in the last stage. And so what I'm trying to do here is to make it, if I have to do that, if I have to give you a reward at the very end, I'll make the expectation of it exponentially tiny in capital H, and I'll give you a Bernoulli so that it will, in practice, it will always look like 0, unless you take like exponentially many queries in capital H, it will always look like 0.
There
Okay.
here. So the dimension, how does it compare? The dimension, how does it compare to the horizon? Like there. So if I give you a dimension and a horizon, then.
Okay, so the theorem will, I don't know if this is the question, but what the theorem will say is that it's going to be the minimum of D and capital H, the thing that the planner is going to be exponential in.
Right.
So if you give a horizon that is small, or if you give it the dimension that is small, then the theorem won't be able to say much. And it is only the minimum of 2. But I suspect that wasn't your question.
Well, I guess, yeah, I was wondering whether this should be the minimum of D and H or something like that is going on. Somehow the dimension is like, if the dimension was large, we can truncate it to the horizon, right? Like there are 2 cases. Either the dimension is large and then you truncate it to the horizon, or the dimension was small and then you just go with the dimension. Or you could also say, if the horizon was large, you truncate it to the dimension. And if the horizon was small, then you just keep the horizon. So I guess you're working with the second one now. Yeah. So the first action is something like this.
So I guess what we'll do here is like the Q star as you go will decrease, and it will decrease at an exponential rate, but the capital H is the number of steps that it will be decreasing throughout. So that's why the last, the expectation of the last reward is exponential in H, but then the number of JL vectors that you can make is exponential in D, and that's where this comes from, the H and D. And you can always truncate. What's that?
No, nothing.
Yeah. Cool. Okay, so that's exactly what I was going to say next, is that if you want to solve this MDP, solve, like, basically get any policy that doesn't just going to give you near 0 reward and have a big gap. So for any delta sound planner that has like a small delta, some constant, doesn't have to be very small, to solve this MDP, you either need to find A star, which is, one of XP different actions. So you need to stumble across this, and that's going to be very difficult. That's going to be exactly, you have to basically try everything. Or you have to learn from final stage rewards, but they have low signal to noise ratio, and these Bernoullis with tiny expectation stakes about exponentially in H steps. And that's how you end up with the minimum of D and H, because either of these two, if you can do either of these two, you're done. But they are both like exponentially hard in D or H. Okay, that's the idea. And then I have this slide, which is just one slide, but it explains everything, I think. So that was trying to like put everything together in one slide, and you can probably tell I was having a bit of trouble with the margins. Yeah, so here we go. So how do we get? Yes.
If you just go, can you just explain again why the reward for the last stage has to be QStar for all actions? Is that what
Yes. So it's because we have this definition of QStar, very messily written here. So when you are at this last stage, the definition of the QStar will actually have a sum that only goes over one reward, which is going to be the reward that you're about to receive. There's no more game. Like after the last step,
Yeah.
the game is over. So the QStar is by definition exactly the expectation of the reward that you're getting for that stage in action, if the state is it is in the last stage. Sorry.
Yeah.
Does that make sense?
Yeah, and that's only for one of the actions?
No, that's for all of the actions, right? Like the QStar of, so if you take any S in S capital H, that's like a final stage thing, then for a QStar of S and A equals expected reward for S and A, and that's actually true for any policy, right? Because for any policy, like this bit only interacts with the future, but there's no future. It's done.
By the way, so there is a related question of, you said that in the last stage we should set the reward to this exponentially small quantity for the optimal action, and I guess 0 for the others, or no, not really 0. It's kind of like, yeah, that's a little bit like, where is this coming from? Can you explain, like, why can't we set the rewards? If you only care about whether you can identify the MDPs based on the information that you're receiving while interacting with the MDP, you could as well set everything to 0. And
Yes, absolutely. So the biggest kind of challenge here is, how do you make it such that the QStar actually computes? You need a QStar which is consistent, and you need it to also satisfy the linear kind of assumptions with the features, right? So you need to give features, and it needs to satisfy the QStar. So I guess that makes it very hard, because when you have this last stage, you do have to give something that corresponds to a QStar, which is an actual number. And so you can't just say, oh, like everything is 0 there, because that means like, at that point QStar was 0, and then you keep going back, and how long has QStar been 0? Can I identify when? So
I guess
you run into problems.
Features, right? So you could choose the features to be identically 0, then it wouldn't matter. If they are not, then that gives away some information about the theta, which is shared between the different stages, right? So this is where the hardness comes in. That maybe the last stage reveals a lot of information about these parameter vectors through these features, and just like observing the rewards, it's kind of like a bandit now.
Yes, and if you give features that are just identically 0, then I'll make a planner that will say, don't even look there. I'll just look for things that aren't 0. I'll always follow one path that isn't identically 0. If I can't, then you told me that this thing that wasn't 0 is actually 0. So like, if I see a non-zero feature and I can only continue down a path that gives me 0 features, then I know this was orthogonal to my theta. So then I learn that way. And I can always follow, unless this happens, I can always follow something that isn't going to give 0 features. So these, just zeroing things out is actually kind of tricky. It doesn't really save you much. And
I guess the
so,
problem is with the Bellman equation. Then if I zero out the
yeah,
features at the last stage, I could do that on
yeah.
its own, like there's no problem with that, but then
Then you
okay,
just reduce the
because
problem to an h-1
yeah,
horizon. Yeah, yeah,
but
and of course the problem is if you zero out all the last stage things, then that means that the Q star of the previous step will have to equal the reward, right? Because
yeah,
the next stage is going to, yeah. So
right.
yeah. I don't know
So
if
that
I'm explaining this well,
isn't
but I guess yeah, the complexity here is like you got to figure out how to make this into an MDP, which has this Q star property and it has the features as well, and it's not revealing information.
Yeah.
And unless it's like absolutely clear that it's completely zero, in which case there's no, it's clear in that case there's no signal in there. But then I might have picked up on that there's no signal in this, and I always follow paths. The planner can always follow paths that keep containing information that I don't know yet.
Right, right. I'm like, you could zero out Q star as well, but like that is pointless because then all the planners are doing equally well, right? So
Yeah.
that's the other, like you have to create some difference between actions, like some actions need to be better than the others because otherwise the planners can be arbitrarily lazy.
Yeah.
Yeah.
Okay, cool. So I guess I was at this slide, which just it's supposed to explain everything about this. So let's see how this goes. So to get this final stage word, a slow signal to noise ratio kind of thing that we talked about, we introduce a penalty factor for each suboptimal action. So anytime you take a suboptimal action, I'll say that your maximum payout, your Q star, has decreased by some constant factor. And this, this I achieve through some penalty function, right? So let's say you've taken actions A1 to AN, and you got to state S, right? So then I'm going to set the Q star of S and A. A is a new action here. So I've taken these actions already. I'm in state S. And note that again, like because the transitions are deterministic, I don't now have to, this isn't a random parameter. This is not a random variable. It's just a function of all the A1 to AN. But that's just convenience. But anyway, so where was I? The Q star of S and A will be equal to these penalty factors multiplied. So like the penalty between A1 and A2, it's kind of like you can think of it as a distance, but we'll talk about what exactly this penalty is. Between A1 and A2 and A3, all the way to AN and A, times lastly the penalty between A and A star, where A star is this secret. That's going to be your Q star, right? And this is very different from the notation of, but I hope that like you will see the parallels. If not, I mean, this is just more general. So like we'll be able to extend this very, very quickly. And I think it makes more sense intuitively. So okay, let's talk about what the penalty is before we talk about the features, and the theta is also here. But the penalty is this thing. It's not really a distance, but it's okay. So what does it do? It takes the inner product of two Johnson linear Strauss vectors x and y. It adds 1 to it, and it should divide by 2. That is a typo. It divides by 2. Okay, so that's just basically you just remap the inner product to be in 0, 1. That's important because, yeah, Q star, I mean, all the rewards have to lie in 0, 1. So because you only give 1 reward in each episode, that means your Q star has to lie in 0, 1. You don't want it to be negative. That would be very bad. So that's why you don't just take the inner product.
Can I ask a quick clarification question?
Yes.
So if you just took one action, like you just took A1, the penalty is just A1, comma A star. Just the action you took at A1. Okay.
Yes. So initially, yeah, like before you take any action, like if you're in S0, then it's just going to be for any A, the penalty is penalty S0A is just equal to oh, sorry, the Q star of this is just equal to the penalty between A and A star, as you said. I think that's what you said.
Okay, so A star is also conditioned on N.
Sorry, what's that? A star is conditioned on what?
There should, like, it's A star. No? Okay. I wasn't sure if, like,
Is that is just like a fixed action? Yeah, like we choose so many actions, then
Yeah,
we can afford
right.
to have the same optimal action in every state.
So A star, yeah, A star is kind of fixed with the MDP. So you take an MDP, the MDP also has an A star. That's not something you choose. That is fixed with the MDP. And then you choose actions, and then whatever action you choose, like this penalty is going to determine the Q stars.
Okay.
And yeah, okay, so so the penalty goes between 0 and 1, and the important thing is that if you take penalty between two things that are the same, then it's going to be 1. There's not going to be any penalty, right? If you take so that is if you sticking with the previous example, if you're in S0 and you take action A star, then your Q star is going to be the penalty between A star and A star, which is 1. So your Q star is 1. And I already said that whenever you take an action A star, you will get the Q star as a reward, and you will transition to the exit lane. So that's the solution. That's the best policy. The pi star from the S0 just takes A star, it takes 1 reward, and that's the best you can get. And it will always take the 1 reward, and it will always transition to the exit lane. But anyway, that's just a side thing. The important thing is that, like, the penalty remaps the JL vectors to the 0, 1 things. And it's also like an easy linear operation, so we can implement it with linear features. And also, each penalty factor is less than equal to this constant. The constant doesn't really matter, but yeah, and as I said, unless the action that you choose is A star, because also we disallow repeated actions. Like, whenever you take an action, you shouldn't take the same action. If you do, we'll just say you got 0 reward and you're done, and that Q star is the Q star on that action is all 0, because it's basically, we can say that's an illegal action. If you take it, you're done. You're not going to get any reward, but you know this, so you're never going to try taking the same action twice in a row. We disallow that, and because of that, if you look at these penalty factors, these A's have to be different from each other, these consecutive A's. And that means these penalty factors will all be less than this 5/8 constant, unless you take the optimal action, which you can take, and then you're done, and you get the best reward. And so because these are the penalty factors are some constant, that therefore the longer you keep playing, if you don't find the A star, the lower your Q star is going to be at this exponential in age rate. Yeah. Okay. Okay, so that's really it. Oh yeah, I guess now the question is, like, so this is the Q star. Why did we do this? How does it work? What are the features, and what is the theta? So yeah, basically the thing to mention here is, like, the features are stuff that we reveal. So there needs to be absolutely no information in this. And then the theta is the thing that is the secret, and that can contain the A star, information about the A star, right? So we need to implement this game in such a way that it has this, like, linearized feature representation, and it does this thing that we're trying to achieve, that, this Q star that keeps decreasing exponentially. And it's actually very simple. Like, all you do is the past penalties that you have, which is exactly like the row before minus this, you don't have this bit, the last factor, you don't have that. So that is a constant, right? So you can embed that in the feature, because you can tell what the penalty between A1 and A2 is. Like, everybody can compute it. It has no secret in it. So this is a constant. And you multiply this with the JL. So for a feature in S and A, you multiply it with the JL vector of A that corresponds to action A. And then what you do, that's the red bit. And then what you do with the blue bit is just to implement the penalty here So what the penalty does is it adds 1 and it divides by 2. And the way we implement that is like we divide this by 2. And okay, so this notation is we concatenate the scalar 1 and then the like d-dimensional feature, we concatenate the 2. And we have this d plus 1 dimensional vector. Is that notation clear? So if you concatenate these two and then you define your theta star to be also this 1 scalar and concatenated with this JL of A star, then if you take the inner product, then that has to be Q star. And let's check if that's the case. You have, I mean, it should be, but maybe, so, okay, so you have I guess the penalty factor should G multiply the whole thing, and then maybe it will be. Yeah, Chaba, let me fix that while this is actually lifted out to here.
Okay.
Does that make sense?
Yeah, and maybe the
so
one
you're
half,
multiplying the entire. What's that?
the 1/2 should be lifted out, so you're missing a divide by 2 of the blue one.
Yeah. Yes, this whole thing is lifted out. So we have a factor which is the product. Okay, let me try this again. So the phi of S and A equals the product of the penalties. So 1/2, that factor, product of penalty of AI plus 1, and then that will be multiplied by this feature, this concatenation of 1 and JL of A. And the product goes from I equals 1 to N minus 1. And let me get rid of these confusing things here. So that's what I actually wanted to write here. Okay, and if you actually do now multiply this inner product with the theta star, then obviously this like constant is going to multiply everything, and then you're going to have inside, you're going to have the JLA inner producted with the JLA star, that's this, plus 1, that's the product of these, and then divided by 2, that's this, and then and so that corresponds to this bit, right? And then this penalty factors correspond to this bit. So I think I'm convinced that the inner product will actually be Q star now.
Well, it's that quantity, and then you will need to argue that Q star is actually Q star.
Oh yeah, okay,
right.
That's the second bit.
One little small thing. I don't know whether, well, people probably remember that you said that you can't repeat the actions. So how do you define things for repeated actions?
Oh yeah, okay. So I was incredibly sloppy there, but just to like for one sentence, just to deal with the fact that is Q star, and I guess here I just want to simply say that because you only ever have one reward, which you either have if you take action A star, or you have if you reach the end of the state of the episode. So you're convinced that you always have exactly one non-zero reward, possibly non-zero reward, during an episode, and by definition that will be exactly this quantity. Like at the end you exactly get Q star. If you take A star action, then you exactly get Q star as well. And so that should be enough to argue that this is actually Q star that I defined here. Whichever way I would have defined this, as long as I keep giving only one reward, and when I give it, it's going to be exactly, expectation of it is going to be exactly this, then it is going to be exactly Q star. So that just makes it simpler to argue.
Yeah, I guess there are two cases. Either you choose the optimal action, then you go to the exit lane, and that's a different case, and then you receive a reward of 1, and then that's everything is consistent there. Or you choose an action which didn't go to the exit lane, and then you kept doing that, and you stayed in MDP, you go to the end, and then at the end you get this little reward, and that's exactly equal to the Q star.
Yes.
Yeah.
So in either case, the one reward you get before you either finish this episode or transition to the exit lane, the one reward you get is going to be exactly that Q star. And so therefore, when you have this, so when you have this, Q star at the beginning, I said something like Q star equals this sum of rewards. And obviously there's like a pi and there's an expected whatever, but the sum of the rewards will actually be just one reward, and it will be the one reward that you give, and that one reward will have an expectation that is by definition exactly equal to this Q star that we defined. I guess it doesn't help to call both of these quantities Q star that I'm trying to prove are equal. That must make it pretty confusing, but
yeah, the reward is defined in such a way that when you are exiting to the exit lane, it's exactly equal to this quantity that we need to have.
Yes.
And
okay, and to talk about sorry.
Same for the last stage.
Yeah. And then how do I kind of glossed over how to disallow repeated actions. I can very simply either say that the action set that you choose from doesn't include that, but you can say that's cheating because it doesn't have the same actions, but it doesn't really matter, because I can say, like, if you took some action A, to reach some state S, I can say that the Q star of S and that same action again will be equal to 0. And that's how I disallow it. I say, there's a little caveat here. Obviously, this doesn't give you the entirety of the picture. Q star isn't always exactly this. If you take a repeated action, which is illegal, then it's going to be 0. And I'll tell you that it's going to be 0. And I implement it by transitioning to the exit lane with 0 reward. It's very simple, right? It doesn't, as long as I'm not, as long as it's never the optimal action, right? Because I can't do this for the optimal action, because then I wouldn't satisfy the Bellman equation, right? So like I can't just lower the optimal actions payout, but I can lower any suboptimal actions payout. And the important thing is only in that case to not reveal information. And I'm not revealing information because the action I'm doing this for is the repeated action. So like everybody knows what that is.
So the optimal action right away goes to the exit lane anyways.
Yes.
If you can't stay in and repeat it somehow.
Yeah. So like the reason why I never disallow the optimal action is because for the optimal action to be a repeated action, you would be in the exit lane already.
Yeah.
So the first time okay. So I guess these are just details, but it's important that we talk about them because they make things work. I don't know how much time I have, because I was going to talk about 2 extensions, but I don't know if we have time for that. So
we do. We have one question only, and people might have questions at the end of once you're finished, questions to you. But on the Slack, we only had one question for the last lecture.
Okay, so when does the meeting end?
20 after.
20. Okay, 20 past. Okay, cool. I'll just be very quick then. One extension is like, the question is, do we need so many actions? Are we cheating by having like an exponential number of actions? And the answer is no, we're not cheating, because and I'll talk about the result in a second, but it's not really cheating to say that we have a lot of actions, because we still said like the whole MDP can be compressed into D parameters, right? So like you don't necessarily need to try all the actions. It's just, it seems to be the case that there is a mean construction that makes you have to do this. But obviously then like it begs the question, is this necessary for the construction to work? Or can you make an exponential lower bound that has a lower number of actions? And it turns out that yes, you can make an exponential, or in this case, the way I asked the question, no, we don't need so many actions. And there's this pretty recent paper. It has a long name, which has the word tensor plan in it, which we'll talk about, I think, on Wednesday. But it's actually the construction is close to this, and the reason why I explained it in this way with the penalty factors is because this way of thinking about it is compatible with what that does. So this is what this is the bit that we reused, and so yeah, like basically the challenge is, you know, for this you needed a lot of actions, and if you just tried one, if you got lucky and tried the one action that was the optimal one, you would have been done right away. So if you had a smaller number of actions and you tried something similar like this, then that wouldn't work, because if you only have like some small number of actions, I will try all of them, and one of them is optimal, and it will transition me to the exit lane with the optimal reward, and then I'm done, right? So you can't give this like exit lane kind of game over, you did well kind of transition from the first state. You can't even give it from the second. You know, you have to delay it a little bit. You have to delay it such that you won't be able to try everything up to that point.
Yeah, I guess like I was thinking that if you have just 2 actions, then you have to delay it for quite a bit, right?
Yes.
Until
yes.
the number of states is big enough so that you're kind of lost.
Yeah, exactly. So it turns out you can't do this with 2 actions, and that is something we're going to talk about on Wednesday. I mean, okay, caveats apply, but I guess we'll come back to that. But it seems to be the case that like for 2 actions, this is that okay. We'll get back to it. But we can do it with this p. Let p be this d to the power of 1/4. And the reason why we do this is because what we called d is the dimensionality of the features is going to stay the dimensionality of the features, but we'll have p be the thing that we used for the dimensionality of the JL vectors. So we're gonna the reason why we need this conversion between the 2 is because we couldn't do things with like exactly linear, but we could do it with 4th order polynomial, which if you have a 4th order polynomial, you can linearize it, and you just need, you know, like p to the 4th features for that. Dimensionality goes to the power of 4. So yeah, like that's just a caveat, but it's not very important. So the main idea is a couple of them. One is to replace the Johnson-Linear-Strauss vectors with corners of a p-dimensional hypercube. And it turns out you didn't need the JL vectors so much. It was just convenient, but it's not as symmetrical as like corners of a hypercube. But you can do the whole thing with corners of a hypercube because, and this is the important bit, with high probability, the inner products of randomly picked corners will be tiny, right? Like if you just pick corners, it's very similar to what you do with the Johnson-Linear-Strauss vectors. In fact, the way you construct, if you look into the lemma, the way you construct these vectors is you take random features, random vectors, and they will have a low inner product. And so that's exactly what's happening here. We first replace the JL vectors with the corners of a hypercube. And then we say that previously every action was to choose one of these JL vectors, which now corresponds to corners. And now we're going to say it's not just going to be one action that chooses this; it's going to be a round that is split across p steps. So I should call this step p steps. P steps is one round when you choose one corner. And so that's basically what's happening is instead of one big step, you now have p small steps that choose a corner, and then you have some rules, and we're not going to go into the details, but you have some rules that say that close corners cannot be selected in consecutive rounds. This corresponds to not being able to choose the same action twice in a row, and then the other, we have to make it, this whole thing such that the pi star optimal policy will be a simple policy that greedily moves towards the corner that corresponds to theta star or a star. Okay, I didn't want to talk more about this necessarily. And I guess we only have 20 minutes, so I don't even know if we have this extension 2. I guess just to go very quickly over this, there is a question here as well that like, is we talk about online planning here. What if you didn't have the planner? What if you didn't have a simulator? What if you didn't have access to the MDP in this way, and you could only go in the MDP as you see it, but the policy wouldn't be able to look ahead and wouldn't be able to teleport to states and try things. What can you say? Is there something like this construction that you can say about that? And yes, there's this other paper that says that even if you have a minimum gap, which basically just says that there's always a gap between V star and Q star for a suboptimal action, right? Like if you don't take the optimal action, then the amount by which your Q star decreases compared to V star is going to be greater than the non-zero, like a bigger than zero quantity. So if you have this minimum gap, which we talked about at the beginning, I don't know if you remember, we talked about how in the last stage, everything should have a small gap. But let's say if you said like, you want to assume that can't be the case, you can't do that. Even then you can make a construction similar to this work, but then you have to disallow planning and you have to disallow the simulator. And this is work done by these lovely people, and what they found is that what we did with downscaling, you can do that with transitions to the exit lane. And so this is what's happening here is in the blue, you're transitioning things to the exit lane with a probability that corresponds to, you can think of it as that corresponds to the penalty factor that we had. And so the reason why this makes things hard is if you have a planner, then you can keep transitioning until you see a red transition, and then you keep going on the reds, and you end up at the last stages, and then you measure the rewards, and then you learn, and that's great. But if you don't have the planning access, you don't have the simulator access, and you can just you can just play the game. Then with high probability you will end up in the blue thing sooner or later, and then that's going to be the exit lane round. So I don't know if that was clear, but that was just something I wanted to point out, that there's this other implication. I think a rather important implication here, that there's this exponential separation between being able to use a simulator and not being able to use a simulator in terms of the number of times you have to interact with the world. So it kind of motivates why you might want to, why you should care about, having a simulator. And if you do have a simulator, why it's absolutely essential to be relying on that, because in some cases it can give you an exponential separation. Okay, that's really all I wanted to say. Yes.
Yeah, and this is with an online simulator, not like a random access one.
Yeah, so with the online simulator, this particular case, you can solve it by whenever you have a state, so you'll transition on that state with that action a bunch of times, such that until you first see a red thing. So you can solve this in polynomial time with an online simulator. But
Sorry, so you can
try the terminology here. Maybe Galert is using slightly different terminology. So we were distinguishing. I was renaming things this year, trying to make it more sensible. So there was local access. So there is online planning. We are talking about online planning. And then there are different access modes to the simulator. And the strongest access was random access. Like you can choose whatever state action pair. The next one was local access. You can reset to previously seen state action pair. And the next one was online access. So with this terminology, so what is this separation, got it?
Yes, it turns out I don't know what I'm talking about, but this terminology, if you have local access, it seems you can solve this in polynomial complexity, because with the local access you can dequery some transition that you've seen. The only thing you can't do is you can't teleport to anywhere, but you don't really need that, because to solve this, what you need to measure what the Q stars are at these things. If you can get to any of these,
is that the random dynamics is not too random. So with constant probability, you are going to the exit lane. And it's not like that, it's exponentially small, the probability of staying in the red node. So like going to the red nodes. But it's like with
Yes, it
constant
corresponds to the.
you're gonna transit to a red node. So you don't have to try the same action too many times to actually see a transition to the next red node.
Right. So yeah, because we need to retry multiple actions at a state that we were just at, right, with the simulator. So if we just have like the online one where we can't reset back to the state we were at, then we're stuck with the same problem
Yes.
as in the online setting.
Yes, if you can't reset, then
Yeah.
if you're in the online RL setting and you can't reset, then you will end up in the blue thing with high probability. But if you have a local access online planning model, then you can always, you have a state action and you can always query it. Like you will only have to query it a constant number of times to find a red transition that stays in the red region, and that's
Just
Yep.
So maybe it's worthwhile to also discuss what would you do if you have a random access simulator, because that will reveal a lot about like, okay, so maybe going from random access, like with a random access simulator, how do you solve this problem? That would be the easiest, right? It's kind of not shown here, but the one but last stage or something like the last stage, you know the states which are there. You can just go there
and see the rewards.
and see the rewards. And then
And
once you
because
see
they have a
the gaps are big, so you get good signal to noise ratio. You estimate the parameter vector, and then you know everything. And so the only challenge then is to get to the last stage states, and that's why you want to stay in. And with the local access simulator, that's not hard. With the online access simulator, that's going to be exponentially hard. Okay. Right? Good.
you mean with the online model, online RL model, it's going to be exponentially hard.
Yeah. Well, I call it online access. If you
Yeah.
if Vince is using
I
a
need to learn the
Yeah, actually,
I'm not good
another
at it.
like with this online access simulator and just the online RL setting, what is the difference? Is there a difference? I guess in the online access simulator, you can just like roll out a whole trajectory from the state you're at right now without actually making a decision yet, and then taking the
That's right.
actions. You can do these like Monte Carlo rollouts without
Yeah.
actually acting beforehand.
Exactly.
Yeah.
That is,
So that's more
if you have
powerful than
online area, then you don't
Yeah.
have the luxury of multiple
can't.
routes. Yeah.
Right. You can't roll out these trajectories.
Yeah.
Wait, sorry. So if you have this online simulator and then you do some steps on it, then take an action now in your actual environment, then the state that your simulator is set at will be off from the state that you'll end up in your real environment, right? So is this like clear? So you have the simulator that's online and it's going to have its own transition dynamics and current state and stuff. If you simulate it for some states, then the current state of that simulator is going to be off from the state you will face in your
You still have the part of
environment.
resetting the simulator to the current state of the environment.
Oh, okay. So you can do that. Okay. So
That's the part that you're given. And the other part that you're given is to do the rollout.
oh, okay. So just to if you do some rollout in your simulator and then the state of that simulator is going to be off. Now you take some action in your actual environment and reach a new state, and then you reset the simulator to the current state of your
Yeah.
environment. Right?
You can always sync the simulator to the environment. That's one part you have. And the other part is to tell the simulator, take this action and then move your internal state to the next state.
Okay, cool. Thanks.
But won't that still work in this setting? Because then, like, we just needed to be able to reset to the current state and retry the same act or different actions. So even with the online simulator, can't we just keep syncing back to the current state and then try different actions?
I guess you have to commit to one at some point, and then you won't be able to reset to the previous one. Is that, if I understood this well, but maybe I didn't. But if you have this online model, then you can do as much planning as you want from this state, but eventually you have to commit to an action, and then take whatever transition is given to you. You can't like undo that and try again. And
Yeah, in the real environment there is no undo.
So like at that point you won't be able to like be set to the previous one and try transitions until you you see a red transition. And if you have like this, you can only reset to the current state kind of thing, then you can try multiple transitions, and you can maybe ensure that the first one will be red, but eventually one of the ones down the line will be blue.
Right.
Yeah.
You're flipping many coins. One of them is going to be heads. And then you're in exit lane. If you do this for a long time, surely you're going to end up in the exit lane no matter what you do.
Okay, maybe I should stop sharing, or because we've got 8 minutes left and there's another question. Or if there's other questions here, I mean, I don't know, Chabot, you tell me what should I do?
Well, if there are other questions for Galed, then let's do that first.
Okay. Go ahead.
Sorry. Can I ask about the hypercube part that you were talking about? So
Yes.
you said that we basically divide these in like p small steps, right? To get like one particular action. Is it similar to like options in like macro actions and options?
Oh, right. I mean, I guess you could think of it like that, but it's yeah, I don't know if this like analogy goes super deep, because yeah, with that you want to think of like time abstractions and all that, and like yeah, I don't know how useful this analogy is, but yeah, you can think of it like that. It's basically rounds, and for every round you basically chose one action, but it's just figuring out how to do the dynamics of the round itself, such that even within the round you have this QStar. And I didn't even talk about that part. Like how do you make it such that even within the round, the optimal policy does this QStar thing, which is realizable. And yeah, like there's some intricacies there, which is why it ends up being a fourth order polynomial. But I guess what I said, which is the interesting bit here, is that you can, these kinds of constructions that use the JL vectors, you can use random hypercubes, and it depends on what your problem that you're thinking about. Like if it requires more symmetry, where in some cases it's simpler to think of it as like random hypercube corners, and in some other cases it's simpler to think of it as JL vectors. So if you're doing something like this and you want vectors that have small inner products, then you can think of like either way will work in most cases.
Thank you.
Cool. Okay.
All right. Then I go next. All right, Shuai, do you want to ask your question?
Yeah, like in this proof, we are like from the high probability needle in the haystack theorem, we know that the total query to find out the only path that returns the delta optimal policy is omega k. But the proof seems to divide the queries into different calls, and we only consider the queries of a single call. But this is different from our previous setting. in lecture 6, that we only call the planner once, and the planner interacts with the simulator, do the queries, and then return a single action. So I'm kind of confused about the setting here.
Okay, yeah, I think that, yeah, the lecture notes are very compressed at that part. When I was reading it back, I was like, oh yeah, this could have been written better. So I will try to explain. So thanks for the question. So basically, it's a reduction. We're trying to say, or I'm trying to say, so the setting was that you have approximate QPy realizability, and you have only constantly many actions, and you want to show that still the cost of planning is going to be exponential if both the dimension and the horizon are large. That sort of thing. So we want to say that whatever planner needs to solve a problem with these properties, an MVP, is going to need to issue a lot of queries. And the way the proof is done is that we are trying to reduce this to say that a planner of these desirable properties could be used to solve a needle in a haystack problem. Basically, it would, like, you would be able to use this planner to search in a huge array. And so we want to use the planner to solve needle in a haystack problems. So what are the needle in a haystack problems? Well, it will be just like searching these huge arrays. And for every needle in a haystack problem, we're going to construct a corresponding MVP. And it goes as usual, like just with this huge tree, with this uniform branching. And the leaf nodes are the entries of the array. And then we want to use the MVP planner to search in this array. So we want to solve a search problem. So the search problem has search queries. We can query entries of the array. We can ask, like, okay, is this entry, like, what's the value of this entry? Right? That's the sort of query that we can use. But here we are using this as a tool to argue that the MVP planners are going to need a lot of queries to deal with their MDPs. So we're going to we're going to construct these MDPs such that every search problem corresponds to some MDP. And you have this k different type of search problems. And then given such an MDP, we're going to use the MDP planner to solve the search problem. But we have to completely solve the search problem. We have to point to an entry in the array, like the MDP planner. If you recall, the MDP planner only gives you an action at the state where you're doing the planning, right? And here in the reduction, we use this big tree. So we need a sequence of actions. So we need to query, so we need to use the MDP planner a number of times. For each stage, we want to get an action from the MDP planner to actually point to an entry in the array, right? So that explains that the MDP planner is going to issue many, many more queries. Like, we're going to need to use the MDP planner to solve the search problem. For this, the MDP planner needs to use a lot of queries because it has to choose age actions, one for each stage, to eventually get to a leaf node or an entry of the array. And also, for each of the stages, the MDP planner is, a randomized planner, which is right most of the time, but not always. So we have to boost its confidence. So we're going to boost the confidence by running the MDP planner at whatever state we are at a number of times and taking the most voted action by the result. So we boost the confidence so that, like, even if you have a bunch of actions, doesn't really matter. With high probability, with probability 1/2, you get the optimal action, because This way, you can guarantee that all the way the path that is selected by this boosted confidence algorithm that uses the MDP planner this way is going to have high chance of finding the needle, right? So we wanted to make sure that this holds. So now we arrange for this to hold, but along the way, the MDP planner was issuing a lot of queries, right? So all what we can say is that in order to solve one instance as a search problem, we had to issue so many MDP queries, right? So the exact relation is something like that. If the MDP planner issues, say, Q MDP queries on expectation in the worst case, then by its construction, this array search algorithm is using at most h times log h times q queries, array queries, because for each, we were counting array queries, right? Because we're going to have a lower bound on that, right? Because whenever you're going in this MDP, only at the very last step, you're going to issue an array query. All the other steps in the MDP can be simulated without accessing the array, right? So when the MDP planner is running, we also need to somehow provide it with the data that allows it to make the transitions and see the rewards. We can calculate, we can spit out the transitions and the rewards for every internal node of the tree without consulting the array. The only time we need to consult the array when a transition in the last stage is made, because then to get the reward, we need to ask the array, like, oh, what's the value there, right? Okay. So altogether, because of this construction, the array search algorithm, which is constructed by using the MDP planner, uses at most h times log h times q array queries, okay? And by the needle in a haystack argument, it has to use, at the same time, at least k array queries. And now if you're putting everything together, then you get that q has to be big. Q has to be bigger than k over. You can't say anything stronger than that. Is this clear? It's because of the nature of this reduction. We really have to take care of two parts of this reduction. Like it's basically what is this algorithm that is searching in the array and uses the MDP planner, and when does this algorithm need to consult the array for values, and how is that used? And then just do the counting, right? I guess like you can think about it a little bit more. The slides are going to be uploaded, and if you have any further questions, then I'd be happy to answer. Although maybe you have questions right away. If you have questions right away, just ask.
Well, I'm confused about how this h log h comes from. Like, it seems like
from, yeah, okay. It's this array search algorithm needs to call the MDP planner h times log h times, right? Because of its construction, by its construction. Because what it was doing is that, well, I guess I have, yeah. You started the root, and from there you want to find out the path that goes to the rewarding node. What you do is that you're running your MDP planner algorithm, and it's going to output some action. Maybe it outputs this. If you only call it once, then maybe it's going to miss. So you call it log2 h times. With this, after you take the most voted action, the action that occurs the most time out of all of these calls, you boost your confidence. Like the probability of missing is going to be not more than 1/h. Okay, so with the probability, the probability of getting it correct is going to be at least 1/h. Right? So with a constant, relatively large probability, you're gonna get it right. If you didn't boost, then this may not happen. So anyways, there is this boosting part of the probability of getting the action right. So after you do this, you find this action which actually gets, which actually is the correct action. And here you have to repeat the whole process because you're trying to get, like, the output of this algorithm needs to be an index in the array. Like it has, like P prime needs to say which entry of the array the algorithm thinks is the entry that has the non-zero element, right? So how are you going to get there? So we get to this. Here we're going to repeat. So again, like log2h times, we're going to call the MDP planner. We get here, and so on and so forth. And this happens h times. So altogether, how many times did we call the MDP planner? We called h times log2h times the MDP planner just to get the output. Okay. Now the MDP planner itself, like how do we use the MDP planner? So the MDP planner itself needs to be fed with information, the right information. So how do we get the right information? Well, we got it from the array queries. So whenever the MDP planner is issuing a query, maybe it's a query, maybe it always queries here in the bottom. Then we're gonna need to ask the array. It may be querying something inside the tree that we don't have to consult the array. But, so whenever the MDP planner is issuing a query, then we need at most one array query, not more, to get the answer to the MDP planner, right? So the number of array queries that we're gonna need is at most q if the MDP planner was using at most q MDP queries, right? So that's why this is multiplied with q. So this is why the algorithm P prime, which is searching an array, is using at most this many array queries, right? It had two parts, this argument. Does this make sense?
Yeah, it's like we're recursively calling this planner, and then we finally get to the leaf node, which costs us h log 2h recursive pause, I believe. And
well,
then
it's not really recursive, I wouldn't say. It's more like incremental or something like that. Like, yeah, we're just making steps and like then move, and then once we moved, we redo the whole thing until we got to the very end.
So another question is, why is log h? It seems like it should be log the number of states.
No, it has nothing to do with the number of states. We want to ensure that the probability of getting this path right is high enough. So the probability of mistake is low enough. So for this, we want to make sure that for each of the stages, the probability of being correct is high enough. And since there are 8 stages, this has to relate to how many stages you have, because, well, at every stage, you might be right or wrong. And so the MDP planner's guarantee is that it's going to get the action correct with probability 1/2. What was, is that true? Okay,
yeah, it was 1/2. I actually have a similar, so yeah, so the story is kind of like, we know that there's these A to the H kind of paths, right? So by that needle in a haystack argument, that's the K value that we know that Q, that that must be done in general by anyone that wants to find that final reward. But our planner is only returning actions for a given step, right? So it needs to do less work. It only it needs to work at each kind of step in this tree. It's not like it needs to return this final result. It just needs to return it. But the way we set up the tree is that there's the number of states. There's a distinct state for each action, right? And so there's these A actions, and then each one leads to its own distinct state, and then it branches off into A more actions and stuff. And like you said, the planner here returns the action with delta probability less than, or with delta less than 1/2. So yeah, I'm just confused by the log h as well now.
Okay, so that's why I have this
yeah.
here, because this should help. So it has 2 parts. Maybe go from the back. I can't. Oh yeah, I could select that. So the end is that at the end, this algorithm that we're constructing is going to return a random action sequence A naught to H minus 1, and having any mistake should have a probability of less than 1/2. This is our goal, because then we can say that we have the guarantee and we can use the needle in a haystack lemma, right? What is that? So just look at what happens if you have just 2 stages. What is the probability that we are making a mistake at any of the stages? That probability is at most the sum of the probability that we are making a mistake at the 0 stage, on the first stage, or conditioned on that we didn't make a mistake on the first stage, we are making a mistake on the second stage. And if we can ensure that in both cases, the probability is less than 1/2h, you can imagine continuing this for 8 stages, everything sets up recursively or whatever, and you get the desired upper bound on the mistake probability. So you see that what we need to ensure is that the probability of a mistake, this is a sufficient condition. If we are ensuring that the probability of mistake is at most 1/2h, we'll be fine. So how can we ensure that the probability of mistake is at most 1/2h? Well, originally it was only 1/2, so we have to boost the success probability. So this is why we are flipping this coin many times. And how many times do you need to flip the coin to make sure that you get the correct result, right? So that explains the log H. Okay.
So for a single call of the planner, the probability of returning a wrong action is a half.
Is at most 1/2. Yeah.
Oh, okay.
But we need it to be 1/2H, so much smaller. Yeah.
So I think
So what's the probability that? So you have to think about what's the probability that if you're issuing so many calls and you're going to take the most voted action, that action is not going to be the correct one. And then you will see this logarithmic relationship.
So why is for a single call, the probability is at most a half? Like we are demanding.
That was the MDP planner's guarantee, right? So the MDP planner. So we said we want an MDP planner that is correct. Well, that is data optimal, and then the data and the two data and so on and so forth are such that an MDP planner, which is guaranteed to be data optimal, has to have the property that it gets the action correct. Like the error probability of it not choosing the action is going to be at most 1/2. Because otherwise, yeah, it wouldn't satisfy this guarantee that it's that optimal.
Right. So yeah, from the definition, we know that the planner must find that final reward. And in order for it to do that, like at the very bottom, it must at least choose that optimal action in each stage with probability greater than 1/2.
Right.
Yeah. So like it's not directly from it, but like it's obviously the case.
So it's like if it didn't choose
Yeah.
the optimal action with that high probability at the very first stage, then it would already lost.
Yeah.
Because
and then we
granted to get a 0 reward, because wherever it gets 0 after that. Right?
Yeah.
Okay. Yeah, it's
Yeah, that
many
makes
steps. Yeah.
Yeah, and then we get like kind of assume the worst case where if it is at worst 1/2, because that's like, then we do this boosting, and then even after the boosting and stuff, it still ends up being exponential.
Mm-hmm.
Yeah.
Right. Okay. It's this reduction to the needle and haystack is happening pretty much all the time. I don't know, Gale, do you think, like, would you say that the construction you were talking about today was a needle and haystack construction? It was kind of a needle and haystack too.
Yeah, it's that, but also like the other part of it was the
part,
low, the tiny,
Signature.
I think that's the two kinds of things you meet, right? Like one is the needle in the haystack, and the other one is when you have to have these tiny gaps you have to measure a lot.
That's right. Somehow you need both.
Yeah, but I think that those two themes are kind of every lower bound.
Yeah, but like sometimes you can get away, with just one of the constructions.
Yeah.
So here in this proof that we're discussing now, we didn't need the signal to noise ratio business at all. It was just needle in a haystack, and then sometimes you need both, but sometimes you only use the signal to noise ratio. Okay. All right. Cool. Then we're gonna meet on Wednesday. Thank you, Gallard. It's awesome.
Cool. Thanks for the opportunity. I'll see you all on Wednesday.
Yay.
Talk about some upper bounds. Okay.
Yeah. Okay.
Cool.
See you.
Yeah.
Bye.
Bye.
Thank you.